Hello, this lecture addresses design documents that are used on a day-to-day basis by civil and architectural engineers. There are literally thousands of different codes, standards, and specifications addressing different aspects of civil and architectural engineering projects. This lecture starts off with a general discussion of what each of these documents is, what their intended purposes are, and how they're developed. Then we'll take a closer look at the documents that address the design and construction of buildings and other structures. There are three types of documents that engineers use on a day-to-day basis in their design work. Codes, standards, and specifications represent the available professional and technical knowledge that is required for completing a project. Codes contain a set of rules or regulations that must be met for new construction to ensure that people are safe. For example, a building code might include a provision that requires spindles in a railing to be spaced such that a sphere 4 inches in diameter cannot pass between them, and that the railing be able to resist a lateral load of 150 pounds at a height of 36 inches above the ground. Standards generally contain a set of requirements that must be met by a product. For example, Bluetooth is a standard that you're all probably familiar with. You don't have to know much about radio communications. All that you need to know is that you compare your speakers with your smartphone if they both comply with the Bluetooth standard. In a structural context, an engineer doesn't need to remember what the appropriate carbon content is for structural steel. He or she just needs to refer to the appropriate ASTM standard to ensure that the steel has a minimum yield and tensile strength. Specifications are a set of provisions that generally address the design of a certain kind of structure. For example, the American Institute of Steel Construction has specifications addressing the design of steel structures, and the American Concrete Institute has specifications addressing the design of concrete structures. The words codes, standards, and specifications are often mixed up to the point where people often interpret them to have the same meaning. I will do that quite often too, but you should keep in mind that they are three distinctly different types of documents. Concern for the safety of occupants in buildings has been evident in the recorded laws of even some of the most ancient civilizations. One of the earliest known building codes is included in the Code of Hammurabi, which was written in approximately 1772 BC, approximately 500 years before the Ten Commandments were written. The Code of Hammurabi says in part that if a building collapses and kills the owner, then the builder should be put to death. Or if a building collapses and kills the son of the owner, then the son of the builder should be put to death, etc., etc., etc. The code is probably best known for its eye for an eye and tooth for a tooth approach, but the code also includes fees for builders and laborers as well. Engineering has come a long way since the time of Hammurabi. Structural engineering is now a broad discipline that involves knowledge from many different fields. No one person can be an expert in all of these fields. The purpose of modern codes, standards, and specifications is to condense that information down to a point where a structural engineer can do his or her job safely without spending hours and hours reading journals and research reports to keep up with new developments. Research is conducted in an effort to advance our understanding of the behavior of engineering structures. That research can take place in a laboratory through a physical experimentation, or could be in the form of numerical simulations conducted on a computer. Sometimes this research is funded by governments through the National Science Foundation or the Ohio Department of Transportation, for example. Sometimes it's funded by trade organizations or foundations. In other cases, research is performed pro bono out of a sense of academic curiosity. In some cases, research is commissioned by private corporations as part of their product development effort. A drug company might pay a university to test a new medication or a vaccine before it's approved by the FDA, for example. That type of research isn't very common in civil engineering or structural engineering, however, because most of the technology that's developed in this area is open source. It's relatively rare to have a new technology in the area of structural engineering that is actually patented. It does happen, but it's not as common as it is in other areas. Those research results are collected in the form of master's theses, PhD dissertations, and research reports. That information is then disseminated at seminars and conferences and is published in peer-reviewed journals. Finally, all of that information is distilled by committees into codes, standards, and specifications with the goal of balancing cost with life safety. Codes, standards, and specifications, which are the resulting documents, thus become the authoritative sources of information for engineers. Most codes and specifications are developed as consensus documents, which means that committees of experts are formed to review research reports, technical papers, and new developments and determine whether changes or additions to a code or specification provision is warranted. Committees are generally composed of academics, practicing engineers, producers and suppliers, and general interest members. This shows a partial list of committee members for the American Institute of Steel Construction. Dr. Rosati and I are fortunate enough to sit on several committees with the AISC. Most of our faculty are active on several code committees. Building codes are broad documents that typically regulate new construction. Building codes focus on life safety and structural adequacy, but also address other issues like architectural details, the construction materials that are used, fire protection, including sprinklers and egress, plumbing, electrical, and lighting systems, heating, ventilation, and air conditioning systems, sanitation, and noise control. Generally, you won't find information on how to design a beam or a column in a building code. Instead, that would be in a specification. The code would, however, include statements like, the stability of a structure shall be ensured. The purpose of a building code is to establish minimum acceptable requirements that are considered necessary for preserving the public health, safety, and welfare in the built environment. Building codes generally contain statements such as shall be instead of should be. The first statement conveys that the specific requirement is mandatory. By contrast, the latter statement conveys that the requirement is discretionary or optional. Development of building codes was driven during the early 20th centuries by special interest groups such as the insurance industry that were concerned with the mounting losses of life and property due to fire. These groups coordinated their efforts to develop a model law or a guide document which could then be adopted by the legislative body to reduce those losses. A building code is enacted by a state or local government's legislative body to regulate construction within a particular jurisdiction and has no legal standing until such time that it is adopted as a law by a legislative body. When adopted as a law, the code's formal status is restricted to the geographic boundaries of the legislative body. For example, if the city of Cincinnati adopts a specific code, then that code is only enforceable within the city of Cincinnati, regardless of where it was written or by whom. Model codes are consensus documents that are written such that they can be adopted by state, county, or city governments as legal part of their laws and regulations. Until about 20 years ago, there were 3 different model building codes in use in various parts of the United States. There are also state and city codes, which may be based on one of the model codes with variations, usually with more stringent requirements. Examples of those include Chicago, Los Angeles, and New York. The Uniform Building Code, or UBC, was published by the International Conference of Building Officials, or the ICBO. The ICBO was founded in 1922, and the first edition of the Uniform Building Code was published in 1927. The UBC was the first building code published and was widely used in the Western United States. As a result, the UBC is best known for its seismic design provisions. The National Building Code was published by the Building Officials and Code Administrators International, or BOCA. BOCA was founded in 1915, and the first edition of its code was published in 1950. Seems kind of odd, 35-year gap there. The BOCA code was originally known as the Basic Building Code, and it was widely used in the eastern and north-central United States. The Standard Building Code, or SBC, was published by the Southern Building Code Congress International, SBCCI. SBCCI was founded in 1940, and the first edition of the Standard Building Code was published in 1945. The SBC was widely used in the South and the Southeast, and as a result, it included extensive provisions for wind loads to address the hurricanes that are common in that region. This figure out of the Tally textbook shows where each of the three model building codes were invoked geographically. This is basically the same figure, but it is shown in color instead. One of the biggest challenges associated with these three model building codes was that an engineer that worked on projects in different parts of the country had to be familiar with several different building codes that all theoretically addressed the same issues. Note that different parts of Texas actually used different codes, and that Wisconsin and New York State used their own building codes. Having this many different building codes was just not a very good solution to the problem. Although the three model codes had been in use for almost a century, there were several drawbacks, including duplication of work by code writing bodies, differences in code provisions, and lack of uniformity in the code format. It's understandable that the UBC would focus on seismic design and that the SBC would include extensive wind load provisions, but the earthquakes aren't limited to just the West Coast, and high wind events don't just occur in the Southeast. Additionally, other subjective provisions in the three codes were different. For example, a 75-foot tall building in San Francisco might be considered a high-rise structure, subject to more stringent design criteria, but the same building in Chicago might be considered a mid-rise structure. To address these concerns at the national level, the Council of American Building Officials, CABO, was formed in 1972. One of the first major achievements of CABO was to adopt a common format by all three model code organizations. For example, you could expect to find provisions covering snow loads in the same chapter of all three codes. The provisions might be different, but at least it was easier for an engineer working on projects in different parts of the U.S. to find the provisions in each of the three model codes. CABO also recognized the need and importance of developing a single code to replace the three existing model building codes. To foster a national unity and allow the construction industry to compete in an international setting, the three model code organizations formed the International Code Council in 1994 with the intent of developing a single set of regulatory documents covering building, mechanical, plumbing, fire, and related regulations. The result of this joint effort was the International Building Code, or the IBC, which was first published in 1997. The main purpose of the International Building Code was to replace the three model codes for national and international use. The International Building Code was built on the common format established by CABO and embodies a comprehensive set of regulations for building systems consistent with and inclusive of the scope and content of the three existing model building codes. In layman's terms, it means that they just took the three model building codes, BOCA, UBC, and SBC, merged them together and agreed on common language and common provisions, and turned that into the International Building Code. The International Building Code established minimum regulations for building systems using prescriptive and performance-related provisions. It has been in existence for more than 20 years and has been adopted to some level by nearly every legal jurisdiction in the U.S. Here is a link where you can access the International Building Code. The International Building Code was developed with the ideas that its provisions should adequately protect public health, safety, and welfare, should not unnecessarily increase construction costs, should not restrict the use of new materials, products, or methods, and should not give preferential treatment to particular types or classes of materials, products, or methods of construction. The International Building Code is available for adoption by jurisdictions nationally and internationally. It is kept up to date through review of proposed changes that are submitted by code enforcing officials, industry representatives, and design professionals. Proposed changes are carefully evaluated through an open code development process in which all interested and affected parties may participate. Now we'll shift gears a bit and turn our attention to standards. According to the ASCE, a standard is defined as a prescribed set of rules, conditions, or requirements concerned with the definition of terms, classification of components, delineation of procedures, specification of dimensions, materials, performance, design, or operations, descriptions of fit and measurement of size, or measurement of quality and quantity in describing materials, products, systems, services, or practices. ASTM International is one of the most well-known standards organizations. ASTM used to be known as the American Society for Testing and Materials, but now they're known simply as ASTM International, probably for trademark reasons. Their standards are referenced again and again in codes and specifications. The idea is that a structural engineer doesn't have time to be an expert in all facets of engineering. He doesn't have time to be an expert in metallurgy, but he or she does need to ensure that the steel that they use on a project is of a high quality and has sufficient strength, stiffness, and ductility to suit the needs. All he or she needs to do is specify in the construction documents that ASTM A36 steel shall be used, and then the contractor is required to use a steel from a mill that conforms to the A36 standard. The committee members that wrote the A36 standard are the metallurgists, not the structural engineer. Similarly, a structural engineer may need to use bolts on a project. The engineer doesn't want to be burdened with definitions of what coarse thread, fine thread are. The engineer just wants a bolt for the project, and he wants the nut to be able to thread onto the bolt. So they would specify in the construction documents that ASTM F3125 bolts should be used. The committee members that wrote the F3125 standards understand the threading requirements and the metallurgy that goes into the production of bolts, not the structural engineer. The American Society of Civil Engineers also publishes standards. One that we'll use extensively is maintained by the ASCE Structural Engineering Institute. ASCE 7-16, the 2016 edition of ASCE's document number 7, is the minimum design loads and associated criteria for buildings and other structures. Now, shifting gears again, specifications should be thought of as recommended practice. They are typically developed and maintained by technical trade associations for each basic building material. AISC and ACI are two commonly used specifications in the design of civil and architectural engineering structures. The American Wood Council publishes a specification that governs the design of wood structures. The American Association of State Highway and Transportation Officials maintains a specification for the design of highway bridges, and the American Railway Engineering and Maintenance of Way Association maintains a specification for the design of railroad bridges. Finally, the Research Council for Structural Connections maintains a specification for bolting, and the American Welding Society maintains a code for welding. It's technically a code, but it's listed here under specifications because it's quite specific to welding. The design specifications are invoked by reference in the building codes. For example, IBC Chapter 19 covers concrete and includes a reference that states, structural concrete shall be designed and constructed in accordance with the requirements of this chapter and ACI 318, which is the American Concrete Institute specification for reinforced concrete. Similarly, IBC Chapter 22 covers structural steel and includes a reference that says the design, fabrication, and erection of structural steel for buildings and structures shall be in accordance with AISC 360. AISC 360 is the American Institute of Steel Construction specification for regular buildings. Okay, this is what the provisions look like in the IBC code. Understanding how all of these documents work together can be very confusing. This slide shows the hierarchy of building codes, standards, and specifications in the design of a typical structure. Why do you have to conform to any of them? Well, let's suppose you're constructing a building in the city of Cincinnati. Now, the city of Cincinnati, in its own laws, provides a reference to the International Building Code. The International Building Code refers to the ASCE 7 standard on the development of loads that structures should be designed for. Also in the IBC is a reference to ACI 318. So if you're designing a reinforced concrete structure, then by reference, you have to design per the American Concrete Institute document. If you're designing a steel structure, then the IBC refers to AISC 360, and you have to design per the American Institute of Steel Construction specification. AISC 360 has a reference to AISC 341, so if you're designing in a seismic zone, you would have to design per that document. So why would one have to design for the ACI 318 specification? Well, the law in Cincinnati says you have to use IBC. IBC says you have to use ACI. Okay, a similar hierarchy exists when you look at the world of bridge engineering. The state of Ohio says that the Ohio Department of Transportation is responsible for the maintenance of most of the bridges. Some of the bridges are owned by counties and by the cities as well. But most of the county and city engineering documents refer to the state provisions. Anyways, the state of Ohio says that the Ohio DOT is responsible for the bridges. The Ohio DOT says that bridges shall be designed in accordance with the AASHTO LRFD design specification using some modifications. So the state of Ohio has developed their own bridge design manual, or BDM, as it's shown in this slide. And it says that we generally agree with everything in the AASHTO specification, but we're not going to permit this type of a product in our bridges. As an example, the state of Ohio doesn't permit a specific kind of bolt to be used. It's permitted in the AASHTO specification, but for one reason or another, ODOT doesn't like it. Another example might be the use of a certain type of construction. Maybe they don't like as an example, they don't like to use galvanized metal formwork in their bridges unless they have to. So the ODOT BDM provides an exception to the AASHTO specification for work that occurs in the state of Ohio. And then by reference, the AASHTO LRFD specification provides a reference to the ASCE standard for some of its loadings. Wind load, for example, is one of those cases. Okay, as an honorable mention, there's a couple of, here's two other documents that are of interest to structural engineers. There are actually several others that come into play, but here are the two that came to mind when I put this presentation together. The first one is OSHPD, OSHPD, the Office of Statewide Health Planning and Development. OSHPD is a group in California that oversees the construction of medical buildings. So basically, if you're going to be designing a hospital in the state of California, your design has to be reviewed by the folks at OSHPD. And in order to ensure that hospitals are designed to the levels that they see fit, you actually have to design it to more stringent requirements. So that's one interesting group. I don't know much about it personally, but I do hear from engineers in California often complaining about OSHPD and how demanding they are in the designs that go into their hospitals. Another one is FM Global. They have a set of specifications for buildings of their own, and I hear about them quite a bit, even from engineers here in the Cincinnati area. FM Global is an insurance company based out of Rhode Island that specializes in loss prevention services and works primarily for large corporations. So why are they involved in this? Well, the International Building Code and the major design specifications are mostly concerned with life safety when it comes to typical structures. That means that if there's an extreme event like a windstorm or an earthquake, those codes and specifications don't ensure that the building will be undamaged. In fact, the goal is basically just to make sure that nobody gets killed. It's expected that the building will likely sustain significant damage or be a total loss, but as long as no one is hurt, then the goal of the codes and specifications is achieved, even if the building is a total loss and it has to be destroyed, several days after the extreme event. When an owner is investing millions of dollars in a building, they might want to have a higher level of performance out of their structure than just life safety. If you're going to invest several $100 million in an Amazon distribution facility, for instance, You wouldn't necessarily want to have to tear that building down after a high windstorm or after a seismic event. So FM Global has specifications that are more that are geared towards a higher level of performance. And if you want your building to be insured by some of these insurance companies, then the building might have to be constructed to a design specification with a higher level of performance than what you'd find in the International Building Code or the AISC specification or the ACI specification. Okay, this concludes this presentation. Hopefully by now you have a bit of an understanding of building codes, standards, and specifications, understand how they're developed and maintained as consensus documents, and understand, at least to some extent, how they apply to the different types of projects that you expect to see as a civil or architectural engineer. Thanks.